All right, so today we continue with Arithmetic of Vectors, 24CC. And so here are some of the things that we have talked about so far with regard to vectors. So let's go ahead and start filling in blank areas. Remember, a vector is something that it's a quantity that has both magnitude and direction. And we typically write a vector in component form. So an example of that would be that vector right there, 5, -2. By magnitude, we're talking about the distance that an object moves. And when we have a vector surrounded with two vertical bars, that tells you that you are going to be finding the magnitude of a vector. So in that instance, that means to find the magnitude of vector v. And I know there's a blank area for dimensional. We'll fill that in just a minute. And magnitude also has direction, and by direction we're referring to the direction in which the object is moved. And we usually use rays or arrows or directed line segments to represent a vector. And in later math courses you may represent those two ideas a little bit differently. And I'm stopping for a second to let everybody get caught up here. Okay, so remember, when we're finding magnitude, and I'm just kind of quickly reviewing how we find magnitude, and since it's referring to distance, we typically find the beginning point of the vector and the end point, and then use the distance formula or the Pythagorean theorem to figure that out. And you'll have a little bit more practice of that in today's homework assignment. And by direction, we're just talking about the movement that the vector moves. So usually it's in the form of north-east, or I mean north-south, east-west, and so on. And then we learn how to add and subtract vectors with the end-to-end method. That was one way that we did that. So that's just to refresh your memory. When we're doing that, don't forget to draw the resultant vector there, which is in purple. And then we also learned how to add and subtract vectors via the parallelogram method, which is slightly different, but once again, we need to make sure we always draw the resultant vector there, and then do some translating to complete our parallelogram. Okay, so now, some more filling in here. We already have the vector part filled in. And now, the new thing. So, scalar. By scalar, we're talking about a quantity that has only magnitude and is constant. I think that should be scalar. Yeah. And the form, since it's just a constant, would just be a number, like maybe 3. And now we're going to go back up a little bit in the notes and write down that a vector is two-dimensional. But a scalar is only one-dimensional. And so to kind of take a look at a picture of both of these things. So since a scalar is just a constant, and this is already plotted for you in your notes, we would just represent it with a dot. So that represents a scalar of 3. And I know down within that graph you've got a blank area or two to fill in. Whereas a vector, since it's two-dimensional, we're going to be moving in two different directions. In this case, 5 to the right and 2 down. And so that is the vector 5, -2. So I just wanted to kind of state the difference between a scalar and a vector graphically. And then in words, and sometimes it's easier if you see things in terms of words or examples. So let's go ahead and add these examples to our notes. Since a scalar is just a constant, and it measures the distance or magnitude 43 miles is a scalar, because that's just the distance. Whereas using that 43 miles northeast, that's a vector, because it has magnitude and direction. Another example of a scalar might be 12 miles per hour. Whereas taking that idea and turning it into a vector may be something like 12 miles per hour west. And another example of a scalar, maybe 50 degrees. And then turning that into something that, in the form of a vector, maybe like 3 miles east at an angle of 50 degrees. So we started this whole process with adding and subtracting matrices. Then we went to scalar multiplication of matrices, and then multiplication of matrices. And then we turned our direction to vectors, and so we've kind of gone through the same process with vectors. So next is scalar multiplication with vectors. So just to refresh your memory, and by the way, I don't think you'd really need to fill in all of this stuff on this slide because this is pretty easy. Scalar multiplication in terms of matrices, you're just multiplying the matrix by a constant. So once again, I don't think you need to fill that in. You guys know what I mean by that. And so an example of that, if we take matrix A and find matrix 3A, that means to take each element and multiply each element by that constant or that scalar, and we get a new matrix there. So the reason why I wanted to quickly review that is because that's really the same thing that you're doing when you're multiplying vectors by a scalar. So let's go to the next page in your notes. In this blank area you can fill in. So to perform scalar multiplication, you need to multiply the scalar by each component of the vector. And if I had not even mentioned that, most of you would have been able to figure that out without me saying anything, because after doing scalar multiplication of matrices, it's really common sense. So if you have vector v represented by the vector, or in component form a comma b, it should make sense to you that 3v would be a times 3, comma, b times 3. You're multiplying each component of the vector by that scalar. So, if you have vector p in component form negative 7, comma 9, everybody find negative 4p. So Bianca, what would that look like then?
That would look like
28 comma negative 36, because you're going to multiply each component of that vector, negative 7 comma 9, by negative 4. And I'm just showing you mathematically how we get to 28 comma negative 36. Okay? All right, so could I get all of you to do 1 through 5? And 1 through 5 are a combination of what we just talked about in addition to some stuff that we talked about last week. So I'll get back to you in about a minute and a half or so. All right, so let's take a look at all 5 of these clearly. Number 1, if vector A is 1 comma 3, 3A would be 3 comma 9. Number 2, if vector B is negative 1 comma negative 5, negative 2b would be each of those components of that vector multiplied by negative 2, so that would be 2 comma 10. Number 3 should be 6 comma negative 7. That's basically back from last week. Number 4 is a combination of today with last week, because today, the today part would be the 2c part, and then you have to take that vector and add on vector A, so that should be 15 comma negative 1. And then number 5 is much like number 4, a combination of today with last week, so that would be negative 6 comma negative 20. Any questions there? That should be pretty easy. And so just like we did with matrices, we're going to prove how this works graphically. So let's go to the graph in your notes on the left, and we're going to do vector A with vector 3A. So let's start by graphing vector A. And vector A in component form is 1, 3. So everybody do that, please. And now, vector 3A, since we already figured that out arithmetically, that's 3, 9. And so 3A would look like that. And I just did it in blue to make it obvious. So notice that vector 3A is, and it should make sense, it is 3 times as long as vector A. And that's what it should be. So that's easy. So when you're doing this in the homework, you're going to need to graph the original vector, the new vector, and then write in what the answer is arithmetically, which was 3, 9, which we had just done. So that's easy. So let's go to the blank coordinate plane to the right of that. And let's graph vector B. Now vector B, as it says right there, is -1, -5 in component form. So that's right there. So let's go ahead and do that. And then vector -2b, which we already did arithmetically, which we would have to do anyway, is 2, 10. Now notice that vector -2b is going in the opposite direction. And the reason why it is because of this. So this is saying that vector B should be twice as long, but one way of thinking of negative frequently is opposite. So basically, this is telling us to draw vector B twice as long, but in the opposite direction. And when you look at the graph, that is exactly what is going on. Okay? All right, so I want you to do exactly the same thing for number 6 and number 7 in your notes. And so each of those should have 3 things. Should have the original vector, like there. It should have the new vector arithmetically and the new vector graphically. So 3 things, the 3 things that I just circled. So I'll get back to you in about a minute or so with number 6 and number 7. All right, let's take a look at both number 6 and number 7. I can see by number 6 that the vector -3x better be 3 times as long as vector x, but going in the opposite direction for the same reason that I just referred to that in the previous problem. So here is vector x. I just figured out -3x arithmetically. It should be -6, 3, and you can see that it is going in the opposite direction, and it is 3 times as long as vector x. So make sure in the homework that you're doing those 3 things. Number 7 should just be going in the same direction, but 4 times as long as the original vector z. And you can see that that is what is going on. So that's how to find scalar or deal with scalar multiplication of vectors arithmetically and graphically. But what about vector multiplication? Because that's where we went with matrices after we did scalar multiplication. So let's fill in those blank areas. Vector multiplication is often referred to as the dot product, and that's how I will refer to it. And this dot product gives a scalar answer. And because of that, it's kind of pointless to do this graphically, because we would just be plotting a dot. So how do we do vector multiplication? Well, it's actually much easier than matrix multiplication. So, and this is where we should start writing stuff down or filling in the blank areas. The dot product of u and v is this. So write that down. So the dot product of u and v is equal to u sub 1 times v sub 1, when u sub 1 and v sub 1 are right next to each other with no mathematical symbols in between. That just means multiplication. Just like AB means, or refers to A times B. So we have u sub 1 times v sub 1 plus u sub 2 times v sub 2. So what does that mean? Well, let's take an example. Number 8. So if we have the vector in component form 4, 5 times vector 2, 3, we would be multiplying the first component of each vector and then add to that the product of the second component of each vector. So in other words, 4 times 2 plus 5 times 3, and most of us will be doing all of that math in our head. 4 times 2 is 8, 5 times 3 is 15, 8 plus 15 is 23. So the dot product between those two vectors is 23. So can I get all of you to go ahead and do quickly number 9, 10, and 11? Add to all three of these. And one way to think about this is in terms of a row times a column, like in matrix multiplication. But anyways, number 9, we're going to have 2 plus negative 2, which is 0. Number 10 will be 0 plus negative 6, which is negative 6. And number 11 will be 3 plus negative 8, which is negative 5. Now, I purposely made one of these answers positive, one of them 0, and at least one of them negative. And here's the reason why. Because this idea of the dot product tells us a lot about the angle. And I'll come back to why that's important in just a second. But if the dot product is positive, like in number 8, that means that the angle between those two vectors has to be acute. In other words, it has to be less than 90. And if the dot product is 0, like number 9, that means that the vectors are perpendicular. So the angle between them would automatically be 90 degrees. And if the product is negative, the dot product, like in number 10 and 11, that means the angle between them would have to be obtuse. So it would have to be larger than 90 but less than 180. Now, why do we care about that? Well, we care about that coming back to why we graph vector, or one of the reasons why we graph vectors to begin with. And that's because there are some cases where we might be asked for the angle between those two vectors. And so when we did this a couple of lessons ago, I gave you that formula right now. And so right now, look, we know how to do the majority of this. This says, find the dot product between u and v. You now know how to do that. The double vertical bars mean magnitude. So the magnitude of vector u times the magnitude of vector v. You now know how to do that. So the only missing piece here would be how to deal with that, which you would need a calculator for that. But that's actually the hardest part is already done. You already know how to do the hardest part. The rest is super, super easy. The inverse cosine part is easy. So once again, the angle there is 110.2 degrees. So now you know how to do about 90% of finding that angle. Okay? All right, so we are finished. You know where the homework is. Go ahead.